welcome back to the Mind Seminar for this semester. So we have great line of speakers throughout all the semester regarding optimization, machine learning, statistics, graph, neural networks, anything related to machine learning and the research interest of our faculty members and students. Again, like any previous semester, we are offering discussions during the seminar. Our first speaker is from Johns Hopkins, so he's local. Feel free to brief him as much as you can. He's a new faculty member in applied math and statistics. And of course, you can see the name there is Case Young. And he did his PhD in here in Baltimore in the physics and astronomy department. And his research interests are in machine learning, statistics, and anything related to data science really. And today, he will speak about the lessons learned during his career after this point on machine learning systems.
Modulo, internet teacher. Yeah, just trying to reconnect to the Zoom. I don't know whether Zoom people can hear. Can people on Zoom hear us fine? Do I need to speak into the little mic and
Yes.
say something? One time.
Yeah,
Okay, fine. So they can hear me fine, I imagine. So I'm just trying to reconnect. Wilson, by any chance you have a computer?
Yeah.
Is that a MacBook?
Yeah.
Unfortunate, but I will use that. Because like my slides are online. I do a lot of things. Why there's internet issue and wasn't pulling up my slides on the internet. Can you connect to Zoom and just share your screen so I can?
Yeah.
Yeah. Again, I can do a brief introduction of myself. And a quick rundown of what I'm going to talk about and like the vibe of seminar that I like to give. I'm a very informal person. Back in my earliest stage of my career, yet an unknown era occurred. I understand. Early in my career, I like to give like very technical talk. I was really drilling down to specific things. I'm going to explain that very clearly. And I found myself in a situation that every time that I'm in a room with like 30, 40 people, there'll be 5 people that understand what I'm talking about and interested, and the rest is like, even though I explain things fine, using it being order. Thank you. Let's see. Go to my get stuff. Okay. Yeah. All right, let me quickly share screen so then and continue to talk. Can people see my screen? Yes, people can see my screen. Can I press that? Yes, too. This is not what I'm talking about today. This is just JQ seminar. Everything that I do is open source online as much as possible, except when internet stops working, then I need to ask for another computer. And formatting could look a little different. But okay, here we are. You can find my slides and all the material on my GitHub. It's under my unhinged presentation. And there's instruction on how to access my slide. So if you want to point to a specific thing or look at the slide ahead of time, feel free to do so. Unfortunately for Wilson, he won't be able to look at whatever he has to do on his computer. Bring myself. So I just want to talk about a couple of things of myself. I'm very informal, so bring me up whenever you want to. And as Nicola said, I did my PhD in physics department at JSU. Before I think it's gonna be Plan B. But it was me in my graduation party, and I used to have very long hair, and I think that's pretty cool. Now I'm an assistant research professor in AMS, but I'm also half paid by DSAI as a software engineer. And so by contract, I'm supposed to solve the software problem. More than that, I'm helped designing the machine that we're gonna onboard, and we're gonna open it up to the institute relatively soon. So if you have any concern related to computing resources, what software you want to get on, talk to me. There's relatively few people in the group now, so I'm a pretty good point of contact with them. In terms of research interest, I spend 20 and 30% of my time on domain science research. That is to say, most of them go into astrophysics, some of them go into material science, some of them go into whatever wacky thing that I'm doing. But I do care a lot about domain science and making things really work on the ground. Not only I need to do proof of concept, which is the theme in this talk, but I also care really how do we solve domain specific science to do better science than anyone has done before. The second thing that I'm contributing my time a lot on, based on mostly my position in AMS, is I spend a lot of time thinking, and not just thinking about theoretical methods, but also code, software. I think about whether things are practical, whether things are useful, but also I do think about guarantees and stuff. And you see some of that in my book. And the rest is really helping out others. And I put it here in the same importance as the others. Is like, I do my stuff, but I have great deal of interest in helping others out. It's not just, oh, I have this driver issue, can you install it? That's not the class problem. I can solve it. But more importantly is like, if you have a workflow, if you have been doing something, oh yeah, we've been doing things in this way, but maybe you're not aware of some new method or some software practice or some computing techniques that you can use. I'm really glad I can help people on that in my previous job, and I'll be glad to help people here as well. So no matter if student, postdoc, faculty, I'm happy to chat in terms of like computing issues. Not just like, oh, my internet doesn't work. Okay, we can fix that. But more like, how can data science, like, we put some of the emerging machine learning technique into your research and really solve state-of-the-art problem. So I think I put a clickbait title and abstract because I didn't know what I want to talk about when I submit the abstract. But basically what I'm going to talk about is like a couple of lessons that I've learned by applying machine learning to gravitational wave, and a couple of things that it's useful, hopefully. But let me just talk about what gravitational waves are. So gravitational waves are these black hole, or not necessarily black hole. If I wave hand like this, there will be gravitational wave that is ripple of space-time. And this is kind of an animation showing the first gravitational wave event we ever detected, that is in 2015, that lead to the confirmation of that. And basically, that is a fundamental feature of space-time or gravity. If I wave my hand like this, I'm like blasting you with gravitational wave, but you don't feel anything just because of how stiff space-time is. This animation shows that like it's a reenactment of these two black holes in a very distant universe that collide and generate huge gravitational wave that we measure it on Earth. And it translates, I don't know where the sound will come through, but let's see. It does not. So this is like band filter and all that, but this is the first sound of ripple that we, the ripple of space-time we heard ever in human history. So if you look into the strength of this, so these two black holes in a distant part of the universe collided and generated this wave through space-time, affected something on Earth, and the effect is 1 in 1,000 of the size of an atom, like nucleus. So it's extremely small. You need to have like really violent event in the universe to make this happen on Earth, that we can see something. So all that is to say, gravitational wave is extremely weak, is extremely noise dominant, and we often see these kind of properties in a lot of fundamental science application. Things are really noisy. You really need to push your accuracy all the way down. You can't just say, oh, my thing is 10% accurate. Like, that's trash. You can't do that. Imagine like this thing, right? 1 in 1,000 of the size of an atom nucleus. That's so small. I can't even have to show you how small. We don't feel that, right? You didn't feel blasted when you were in 2015 by gravitational wave. So there's a couple of things that we've been thinking, or not thinking, people have been doing in applying machine learning to gravitational wave as a field. So people do searches, okay? So as I said, we have detectors on Earth that can measure that tiny little signal, but there's so many things that happen on Earth that can contribute to disturbance in that detector. Like for example, like a truck drive by, like 40 kilometers away or 4 kilometers away from the detector, we can pick that up. Gravitational wave detectors are extremely sensitive seismometers as well, but we don't want it. We don't want like a Mercury earthquake. That's interesting to some people, not to astrophysicists. So there's search problem that we look into our data pipeline. There's all these glitches. None of them are signal that we're interested in. So there's an interesting machine learning problem. How do we search for event effectively? And then there's simulation problem. So later on, we're gonna get into that. But because of how small the signal that we're looking in and the dominance of noise, we rely on something called mesh filtering. Basically, if we know what we're looking for, we can kind of filter out the nonsensical junk out. So this is just a simulation that people made in the past that's showing you two black holes going around the curvature of the space-time underneath it, and it's generating this signal that ultimately we're going to say, this is a model, this is not what we see in the detector. But with these models, we can effectively dig out our signal in the data stream. So this is important. People have been doing it. We've been thinking about how to use machine learning to enhance this process. We're going to come back to this later. And finally, there's something that, oh, wait, important part. All right, that's too slow. There we go, look. Okay, that's fine, whatever else is important. Anyway, so but one thing that I myself care a lot is inference. That is, like if I give you the data and I hand you a model, can you tell me something about the properties of the underlying, you can see the gravitational wave going on, underlying process, like what's the mass of the black hole? And that is an inference problem that I give you some data, you have some mental model, now you got to figure out what's going on there. So that's inference, and I care a lot about that. So we're gonna talk about that. So the theme for today is like it's just really me ranting. I'm gonna give you my opinions. They're not true. Very likely to be wrong in some of the situation, but it's just some of my take and my experience with interacting with very fundamental science, astrophysics. Nobody gives a shit, right? It's something like dust but far away. So fundamentally, if no astrophysicist alive tomorrow, will people die of cancer? No. So it's not something that is very practical, the subject itself, but it has a lot of interesting properties that if you apply machine learning that was found on like PyTorch.com, you run into trouble. So I want to give some of my opinions on how should we think about when we throw machine learning on these fundamental science things that is like super wacky. Second, there's no deep math. I've been looking through the list of topics of past talks, and people always talk about deep math. It's like, oh my God, I don't know any deep math, so what I'm gonna do? So I'm not gonna talk about any deep math. It's mostly just opinion. If you're looking for deep math, we won't take any of them. Hopefully the most important thing is I'm here in Hopkins, so I'm gonna be around for a little bit. And really this talk is for you to know me. Like what am I interested in? What do I do? What is my strength and maybe weakness, cursing too much? So if you have problems, we'll totally chat afterward, and I'm happy to do so. Alright, so I have 3 lessons to give out because like I think in the abstract was so when I get the email memo, it's like, oh, you are giving this lecture. It's like, wait, when did I sign up to give a lecture? I didn't sign up to give a lecture. I didn't have like great wisdom to give out. So, but anyway, I'm going to put them as like lesson 1. Be aware of the text. Be aware of the text. So let's be a little bit more precise of what do we mean by inference. So the first part is about inference. Inferring the source properties in this context of gravitational wave is the following. So our data is essentially time series. And I'm just showing like some simulated data here, and this is the data channel. So the blue line here, like the deep blue here, is like some white constraint, they normalized in some way. What your detector will see. So you have a lot of very, very noisy signal here. Extremely uncorrelated, extremely complicated. And the cyan line is what we want to dig out from the data. Okay. So if I don't plot the sign line here, you have no idea it's hidden there. So it's already, you can see how complicated this is. And actually, this is already exaggerated in the sense of comparing with the real data. The real data is probably about 10 to the 6th order. If you look at just the raw data versus signal strength, it's about 10 to the 6th order, 10 to the 6th order of magnitude about the signal usually. And the task that we want to do is I hand you this data, I give you some model. Now tell me what are the mass of the black holes, right? Simple task. Trivial. This is $1 million problem because so far we have detected 100, it's been released 100 events or so. Each of them costs about 1 million CPU hours, I would say, to solve this problem. If you think about it, this is pretty dumb, right? I give you a time series and so ask you to find some wiggle. Somehow these people need to spend 1 million CPU hours on finding this. Why is this so hard? And if you go to Google and look it up, it's like about $0.01 per hour if you want to use like AWS or something. And that translates to $1 million problem. So if you can solve this fast, we save $1 million. I always advocate to give out a prize that to whoever solved this problem should take the money. They never listen to me. I solved the problem. And why is it hard? And it's hard for a couple of reasons. And one thing is the posterior can be very multimodal. And when you hit multimodality, everything becomes hell. This is my word for it. We can explain later. But here is the possible sky location of where the first couple events comes from. So if you're on like North America, that we have our detectors here, and it's basically either above, like directly above like us, or like all the way on the other side of the Earth. And you can see the uncertainty, like these are the confidence interval of, like, so basically where do we think these events are and colored by different events. You can see like they span a great deal on Earth, right? Like, from let's go to the sky. So if I say, oh, let's hang out, where should we go? I mean, in this region, it's useless. It's not gonna fly. So that's one problem of multimodality. We can either hang out in America or like in Antarctica. It's like, okay, that's not very useful. The other thing is, our prior knowledge about the system is extremely like unconstraining. Let's put it that way. We know the mass cannot be negative. If you have encountered any negative mass system, let me know. We can go get a Nobel Prize. But so here is actually the posterior of some of the event. Okay? And the square is our prior. So our prior is like, I don't really know what is the mass of my event. So I need to search kind of through this space. And this line is actually a confidence interval. It's not a line. It's actually a contour. But in some spaces, multimodal is very broad. In some space, it's extremely narrow. So you need like, and there's a lot of like local minima in between, it's like hiding on context and whatsoever. So to go from like here to there is extremely hard. You need to hit that creep. So in some cases, too broad, and in some cases, too narrow. So gravitational wave is actually a very hard problem in general, because sometimes if you just miss by, let's say, I don't know, 0.0001, then you're off. And we do not allow that. We're like scientists, we care. Okay. So hopefully you see how hard gravitational wave is. And here's the machine learning bit. So people have tried to solve this problem in multiple ways. There's the traditional method that we build a model and then we do MCNC on top. That's like a traditional method. But one thing that people have been doing is like, why don't we put AI on top? So what people have been doing is they simulate, like this is not necessarily in gravitational, I'm just drawing in physics in general. This is a very cheap thing to do, okay? So we have some simulation. Let's say if I care about galaxy or cosmology, I'll simulate that. AI happen. I get what I want, right? Here's the same thing in particle physics, right? Where I have my very complicated model of my detectors and particles and so on and so on. AI happens. And then, I have my posterior again. And this AI happens magic, whatever we punt to the AI expert, is called simulation-based inference. And why we're doing that is because generating the simulation usually takes some time. And in some situations, they could be very expensive. For example, in simulating like our largest particle collider, it could be very very expensive. And what's even worse is writing down an explicit likelihood that you can later on throw into MCMC is even harder. But people can simulate. So what they do is like, okay, I have my data. I plug something through a sample, basically sample my simulator through this whole machinery. Then I just directly see whether my data looks like my model. If it is yes, I accept it. And if it's not, then I reject it according to some criteria. You rinse and repeat, and after a while, you're left with a bunch of points that your simulation looks similar to your data. And whatever doesn't look similar is get rejected. So you're left with a point of what is the truth. So people basically, there's different techniques into that. We can go into the detail. There's normalizing flow, gang, whatever that you can think of it as hip in machine learning. People have been doing that. So I mean, I'm not going to go into detail. If people interested in detail, we can always talk about detail later. As I mentioned, I don't like to talk about detail in a broad talk. But concept is like, and the idea behind detail is more important. So this has been working quite well for gravitational wave. This is like a aspiring, student, has nothing to do with a good friend of mine. I always review their paper. I'm pretty sure that they always put me as a referee because they know I'll give them a good time. But Max is dudes from Germany that they've been, taking this gravitational wave model and taking the different instantiation of noise, just train this machine learning thing, right? And you don't need to go into the detail of like knowing what is going on, but basically there's a ground truth behind, right? That is blue, and they have this AI thing that you give me the data, you process it with this AI thing, it looks the same, right? And they do it. So I think in this paper they can pull out the result in 10 hours GPU hours. Okay. Whereas in the counter example, it could be thousands, millions of CPU hours. So they speed up a lot. Awesome. I like their work a lot. So that's why I put them here. And people seems to have solved the problem, right? Like gravitational wave data is in posterior out. Awesome. Now, that's been working. The second thing that I want to I'm jumping a lot here, but that was the first question I showed you. If I give you the time series, can you tell me what are the masses? But one thing that people are also interested in is, if I give you a bunch of gravitational wave event, now can you tell me something about the properties of the population as a whole? Okay, so there's different way to form black holes. There's black holes that are loyal to each other, they spend their whole life with each other, and the black holes kind of, I don't know, coming in and out in a relationship and forming wacky stuff. So there's different scenario of generating a distribution of black hole. Now the question becomes, if I give you a distribution of black hole, so instead of giving you a time series, I give you a distribution of black hole, can you infer which one of them are loyal to each other, which of them are not loyal to each other? So I did that. And again, the same story, like generating simulation expensive. So we do it ahead of time, and then we just compare with the catalog of gravitational waves that we have. So this is a paper of mine that I did when I was a grad student here. And basically the idea is we have this different simulation, cosmic CMC whatsoever, that they generate distribution in masses, okay? And it's pretty expensive when we train some normalizing flow on top. And at the end, we get posterior, okay? Now, it's the same team, right? Both are simulation-based inference. The first case here, I give you the time series, you give me the mass. Second, I give you the distribution of gravitational wave event, you tell me which one are loyal to each other, right? If you believe us, then most of the binary black holes that we have so far are from clusters, this object that have a lot of black holes in it. But the thing is, after I publish the paper, it's wait, everyone get excited, and it's wait, this is bullshit. I mean, it's not like it's wrong, but it's fundamentally broken. I don't know what was the term to put there, but it's something's fundamentally not right. Let's think about it for a moment. I mean, for most of you won't really see why there's a problem here because you're not a domain expert. But there's a moment, the procedures are similar. Just like anyone here would have done for any other paper, my procedure is similar. data comes in, train the transformer, something comes up, publish a paper, do it again, right? Simple. And we just did the same thing, right? You know, simulation-based inference, data comes in, normalizing flow, posterior comes out. Let's move it to the next task and do it again. But, and then like after I marketed it so hard to, like, well, I was a grad student, I need to get a job. So I marketed it so hard, everyone like super hyped about it. And then once I become a postdoc, I told people like, don't do it. Trash. Now, why is that a problem? Why is the first example is more believable? The key difference are, well, actually, let me just, this one. So before we go into like the key difference, I'll give you a moment to think about it. But here are some perks of simulation-based inference. Very, very fast inference, right? You see this in a lot of like machine learning workshop, predominantly workshop, conference is a little bit better. But they will emphasize that, oh, we speed certain things up like factor for like 200, something, right? Very, very fast inference in general. Like human, you know, it's the grad student who tuned this stuff. It's not me that who tuned this stuff, so who cares, right? Like the retuning effort is like pretty similar. And once you have like your weights and biases run set up, you just click a button. You change something, click a button, you know, things retrain, isn't that happy? And it really allows a lot of like flexible assumption. That's why, you know, simulation-based inference, these surrogate models are good. It's like it doesn't depend on something that you work on for years. It's just like, okay, you change one part of the simulation, you can swap that in and out. Now, the downside of, well, this is, I'm saying SPI here, simulation-based inference here, but really, it's something that I care a lot in machine learning is like some dangers associated with these class of method. Whenever you have like a black box inference machine. First of all, like, why is my math negative? Right? If I give you data and you train this machine, your student tells you, we assure you that it works very hard, and every validation that you could do is functioning. And then you look at the results like, well, but why is the math negative? And it's like, no, this is fine. You know, we use the latest model, this is fine. What the fuck? This makes no sense, right? So the machine learning method in general, they don't necessarily respect some fundamental principle unless you bake them in. Okay? And so that's one of the main danger. The second is, are we really winning? Especially for some of the PIs here that need to fight over GPU. It's like, yes, like retuning effort from human is pretty low, but you need to subscribe to that GPU and you need to pay a certain amount of money to get the thing running again. So if you have a bug, you have like some model changes within your scenario, then you need to train again. Are we really winning? If you train every time to get the new result, can we do better? And finally, it's just like I want to get back to like GPU is expensive these days. I need to like keep harping on that. The main difference now is here comes the answer. The main difference between why scenario one, I'll give you the single event inference, is more reliable is there, the model is actually fixed. So we only have like numerical relativity. General relativity has been correct for 100 years. So we're not changing that. The data is continues to change. Okay, we have like new event coming in. So that's good. We have the same pipeline, we could just keep deploying. Whereas in the other case, actually the community has like arguing back and forth, what model should we use? So we've been like just continuously retraining different model and testing against the same data. Now that's bullshit, right? And if you think about it, that's actually very common these days. If you think about training and like large language model, we've exhausted all the language text that we could find mostly. So we don't have fresh data, we have fixed data. And people have been changing their model all the time. And it's important to ask ourselves, is that what we really want to do? Are we actually gaining something? Or we're just hallucinating in some way? So the first lesson that I want to talk about, like really drive home is scaling the compute easy. Hopefully in this example, it's not very well fleshed out because there's no gravitational wave people here, but changing your model in machine learning is very easy. Right? Like you just go on PyTorch, change the hyperparameters a little bit, you have a new model, right? But unfortunately, if you really want to do something that is productive from time to time, not always, sometimes it's okay, but scaling data is hard. The first thing I want you to think about is like, it's very easy to spend time thinking about compute, but it's also as important, if not even more important, to think about you need to do something about data. So that's the first thing that I want to talk about. Again, you know, any you can call me bullshit anytime. happy about that.
Can I ask a
Yes.
question? So is the output of this method an estimate of the posterior?
Yes,
Or, okay, so somehow you're getting, like, you get confidence intervals and stuff out in this, so I mean, are you running like some gigantic number of these simulations, like kind of on a grid of the parameters?
That's right, that's right.
Okay.
That's why, there's the retraining problem, right? Like, if every time you change your model, you need to run this gigantic simulation bank again. And then you train it, and then you get some posterior out, and you say, oh, the inference is very fast. But like, wait, there's the bank of simulation, now you want to redo. That is not very economical.
I see. So it's like for a fixed model,
Mhm.
you've gone over some like massive, collection of different
Mhm.
possible choices of parameters, you have like a big pile of data of what the output was from those, and then you try to do something variational
Right,
inference
right.
style thing. Okay.
Yeah, so that's why like the message here is, if you just do the big simulation once and you keep deploying the different data, if your bottleneck is the data, do it. But if your bottleneck is the model, think about it. Oh. The second thing is like fast and not enough. Like it's interesting that when Wilson was in some Slack channel, we're talking about that. Oh, when you see the title, it's like case one, hard one, obvious difference. Like no, I want to talk about my failure. That's if there's one theme about like this talk is like about my failure, and because like things are hard when it comes to like medicine. So the second thing that I want to talk about is like fast is not enough. Just to keep an eye out for the time. And as I mentioned earlier, we depends on like our capability to analyze the data depends on the model. And one thing that we use to compute the model is something called numerical relativity. It's this equation. Extremely simple, isn't it? It's like any kindergarten can write this down. Unfortunately, you can like actually unfold this guy. It's quite complicated, and this is one of the simulation that we had. Resolution is kind of crap here, but like it's actually like tensorial equation in the 4D space. So there's about 16 or 18, I don't remember how to count, couple PDE that you need to solve in like a 4D space, not just 3D space, because space time this is working. But yeah, this is two black holes that are like run some years ago. There are two black holes colliding each other, and these are different properties of the space time, like curvature and so on and so on. And you can see as they're about to merge, the gravitational wave comes out. Okay, so solving these guys, I used to use Marcy. Is there any Marcy people here? Did anyone use Marcy? Profit? And it was very great. Anyway, I use it and it was exploding, everything not working. It takes quite compute. I just want a picture of Mars. Anyway, so running numerical relativity simulation, these high fidelity simulation has been the predominant way to construct state-of-the-art model for comparing with the data. Okay, this is just to show you some of the complexity. It takes a great deal of amount of compute to do these things. So not easy task, but we can do it. Now, the main problem is there's all these next generation mission that we have, both in US, in Europe, and in space, right? People are building bigger and bigger detectors. We're gonna throw them into space, we're gonna detect some other thing. And the one thing that people like to talk about when they talk about next generation detector is like, so I mean, most of the audience here won't recognize what these are, but focus on this figure, okay? So these different dots are predictions of where the data could be, like what are the sources of gravitational wave in that entire universe. And these lines here are the projected horizon. So like whatever within it, we can see it for next generation instruments. And if you look at this, this is actually a pretty cocky statement. You think about it, is like, this is to say in the entire universe, observable universe, whatever thing merged, we will see it. I don't think anyone has made that statement ever until have some lunatics from gravitational waves start talking about that. It's like whatever, as long as our instrument is operational, we will detect it. So it's great, it's great promise. Our thing is awesome. It's basically at that point you become, everything in the universe. That's crazy, right? The problem is better detectors warrant, like, means that we need better model. So here on the x-axis is like different timeline for different detector, and network SNR is just like the signal to noise of our event. Like, what is the signal to noise that if like a black hole collide, what would that look like in a specific design of like a future instrument? And mismatch is basically your accuracy requirement. So the green band here is where our like the accuracy of our numerical relativity models hold. Okay, so if the green band is above, which way goes? Like it's below the uncertainty. So these lines is basically telling you, oh, if you have an event that with this signal to noise at this time, this will be kind of your uncertainty level from the noise. Okay. If this noise is above my band of numerical relativity, meaning I won't be limited by the model. Is that clear? But like you can see, there is a problem here. In the future, when we upgrade our detectors is going to be so sensitive to these signal that we just cannot rely on numerical relativity. So I spent years into making this bank of simulation, but they're just not accurate enough to be used for data analysis, right? I spent, I don't know, billions into building this amazing thing. Now I'm like bottlenecked by a bunch of theorists. It's like, God damn it, we should have given them money. Right? So better detectors mean that we need better model. And if you look at the mismatch here, which is kind of uncertainty, you can kind of take it as a percentage. We're talking about 10 to the 5, 10 to the negative 6. Okay? And for people to have viewed, especially if you have worked in simulation world with machine learning, this is a crazy number. If people reach this is already like awesome paper. I haven't yet to find people reach these numbers, but here is what we're talking about. So we need accuracy. Now I just want to show you a little bit of like where noise could come from. This is actually a simulation that I made to purposefully crash it. But this is like just a moving black hole. There's not even 2 black holes. But because the black hole is so small, comparing to the domain that you need to simulate, we do something called match refinement. So we put more computing resource and resolution in region that matters. So here is the black hole. Here's the region that we want to simulate. And you can see this boundary between resolution level. So if you let the black hole, we boost the black hole in some way. And so it's moving very fast in one direction. So it's moving this direction. And if you do this, there will be some error propagating in the space. And let's look at this. So you see some error coming from the boundary, but now since shockwaves come here, it'll just bounce back and forth with the boundary. Get it again. And later on, crash my simulation. You see this like shockwave here? It's just like error propagating. So there are like numerical noise everywhere in this simulation. And we need to think about ways to suppress that. Now, like the next slide is going to be my slides of failure. I'm going to play the video. Now, I'm going to do a poll afterward. So this is what I did when I was a grad student, like to try, maybe at the beginning of my postdoc. One thing that, actually, let me go back for a second. So one thing that I look at this problem is that, okay, there is this boundary communication error. Isn't that a super resolution task, right? The reason why there's error here is because you have some data living in a low resolution regime that you want to interpolate in the high resolution regime, but you can't do it faithfully, So there is where the error accumulates. So can we not train some machine to do that interpolation, right? Machine learning interpolation is awesome. So I tried to do that, and I was talking to some people. Who does neural operator here? Am I offending anyone? Who cares about operators? The neural operator. Hands up. I'm gonna say something wacky of this. Anyway, so at the beginning of my postdoc, I was interacting with some people that like is fanatic about neural operator. It's actually the NVIDIA people that I'm talking about. Anyone with NVIDIA? But anyway, so I asked them, okay, we have this super resolution problem. Can we do it? It's like, yeah, look, we have this amazing thing. It's resolution independent. You just put it on. It's awesome. They even say that like, this is not great, this is revolutionary. It's like, oh, wow, okay. So this is some simulation that I generated is the native. There's some ground truth behind, so I take the ground truth simulation, downsample it, and try to train a super resolution tap, okay? And you see it's actually functioning quite well, right? Like, take the downsample, train. This is my network prediction. The resolution on the screen is kind of shit, but they actually looks pretty good. Like just from high. And you can indeed, like I train on just 4x. So this is 4 times downsample. You can train on this and it does well. But it seems like you can push through to even higher resolution, 8x, 16x, right? Who thinks this is working? Just a hands up. Okay, there's 2 people that think this is working. I like more skeptic again. In fact, this is not working. I was trying to integrate this into our code. But first off, actually doing this integration is hard because this runs on GPUs. Oh, you need to use this. But like our code is actually a traditional HPC code that is made in CPU. So they didn't like it, but I spent a great deal of time trying to integrate it. It blows up. So I don't even have the loss cost to show. Anyway, so that's just to say, like, if you have ever come across simulation with machine learning, this is how people do it. It's like, does these 2 images don't look the same? It's like, yeah, they look the same, but so what? It's like human can roughly see, like our image is usually 8-bit. Right? That means that you have a resolution of about like 1 in 100, 1 in 256, so on and so on. That means any difference between these 2 pictures that is kind of below 10 to the -2 accuracy, you won't pick that up. So showing this is garbage. Like, even though it works perfectly here, if you do the residual and all that, they're actually just not good. And another attempt that we've been doing, and this is finally, I think this is 1 year paper that we can submit with a friend that he was a postdoc, I was a grad student. I talked him into doing this when he was here, and he had a rough time, like just because of that idea. He was so enthralled by the idea, and he just wanted to do that. He got fired. Anyway, that's a different story. But the idea here is instead of now that was end-to-end training, but here we integrate some upscaling and constraint minimization. That is to say, if I give you a snapshot of the simulation, you plug it through some neural network, and then you have some residual, and at runtime, so when we're running the simulation, we're trying to minimize some error. So we try to use neural network as a control term in our simulation, and that has been functioning better, but that took what, like 4 years? I didn't do it, the postdoc did it. Not me, just to be clear. And this is just focus on this one. So this is the simulation as as it progressed, and this is the ground level of uncertainty, like constraint violation that we call. It's basically some non-physical thing in our simulation. This is the ground level, and through this we can do some productive thing. We suppress the error of the So that just has been starting to work in numerical relativity. This is just proof of principle, really, but it's starting to move toward the right direction. But that required us to really integrate machine learning directly into the simulation. Anyway, so I really like this min. Just to show that this is what people keep showing. And whenever someone talk about simulation fast, I just show them this meme. That's not useful. You need to be accurate. Anyway, so if you do simulation, I'm happy to talk with people that do simulation with machine learning more. Proof in principle is very easy. I prove a principle to you, right? Like in this talk, I show you that super resolution, awesome, 2 images look the same. That's easy. Making simulation are way harder because we need to integrate it with the full pipeline. We need to make sure that we deliver the accuracy. That is way harder. All right, I think I'm pretty good on time. So finally, I want to talk about something that I like. Finally, actually work. Let's recap briefly. I'm going to go back to inference world for a little bit. Machine like gravitational wave inference, hard, expensive. And instead of doing a black box training or end-to-end training loop, like what the simulation-based inference people did, what I did is the following. Can I do F5? Can I? Yeah. Okay. So this is awesome website, MCMC Gallery. I just want to quickly recap with you what MCMC is about. Autoplay delay, is it this one? Yeah. So the idea of MCMC are like really sampling, any posterior is the following. You have your target function that you want to sample, and you have some proposed kernel that is giving you a headache. Then you transfer this place, just drop points and rinse and repeat, trying to do bias random walk in this space. And after a while, through these like MCMC process, can I close? Okay. Then you're left with samples that approximate your target, right? And that animation should tell you something about these methods are usually local, right? Because you see, like this is called Hamiltonian Monte Carlo. Who knows HMC? Okay, good. Some people know HMC. That's all I need. But basically, they only proposing to move in their local vicinity. You can choose different kernel, different method in MCMC. Let's see if I can find this one. This is like a random Gaussian, but basically, you're just drawing Gaussian around you. These things are local, and that's what actually makes traditional MCMC have a hard time to deal with the problem that we have at hand because things are multimodal, right? So it's very hard to go through individual mode with traditional MCMC. And on top of that, you have a specific kernel size. And if that kernel size doesn't match your target posterior size, you also have a hard time because the posterior could be much smaller. So one thing that I did, this is like more in the math, this is more general, is build a code that it's a class of new emerging method that we kind of call it adaptive Monte Carlo. But basically, this is just to show you some features that backbone interface has like GPU support and all that. Good software, check it out. If you're interested in inference, talk to me. Love this thing. I made it. But here's the idea. So normal MCMC, made it with Matlin by the way. That if you have two mode across, it's very hard to jump across this energy barrier, right? Like there's a huge gap here. If you want to go from here to there, you have to go all the way and go across and go back, right? So if I want to know the normalization across the two mode, it's actually quite hard because it requires you to jump from highly likely region into not very likely region. So you're unlikely to jump into here, but then go back into here. Okay, so crossing energy gap is usually very hard. What we did is instead of just launching one kernel, like one walker in this space, what we did is like as we generate more data, so we launch a swarm of these particles, like walker, that trying to go around in the space to find all the mode. And once they find, some of the mode, they keep generating data, right? Once you generate data, now we train some machine learning to try to approximate the posterior. But the one catch that we use here is not just training, because I don't trust machine learning. If you can't tell by now, I don't trust machine learning too much. So what we did in trying to, when we're building flow MC is the following. So we have a target, it's very hard to go across. We generate some data to try to approximate, but it's not quite correct, right? And we have like some procedure to adjust. We only use this machine learning thing as a proposal, right? We're not trusting the machine learning as it is, but we have some adjusting criteria that will make sure that ultimately things will be correct. I mean, we can go into detail. I don't have that much time, so I don't want to go into detail here. But the catch here is in building flow MC, there's two components. One part, we're still doing normal MCMC. That's been useful, that's been reliable, and been shown to have good properties. Okay? But it is inefficient. So in where it's inefficient, which is the proposal, we pull in machine learning, but we'll keep it there. Okay? We don't just trust the machine learning proposal whatsoever. We actually use it as like just a guess for MCMC. And that have been shown to be more robust. So this is marketing. Yes, I'm not funded by Google. I love JAX. We're gonna make me put this slides in. Yeah, if people haven't heard of JAX, if you want your student to run faster, compute, let me know. I'll put them in JAX instantly faster. Okay, JAX awesome. Ditch PyTorch. Anyway, so we built something in JAX like the gravitational wave model. We fully integrated with Flow MC, and in the end of the day, we put it all together And like this is a similar example of what you've seen earlier, solving the same problem. This is just to show that it's robust and it's not biased. But now we'd be able to push these, like with all the thing engineering effort that we put behind this project, we push the same problem that like the simulation-based inference problem people want to solve down to 2 minutes. Okay, so let that sink in. 1 million CPU hours to a couple of tens of like GPU hours to 2 minutes. And the good thing about this, that if you ask me, I still shit on myself all the time, but this has guarantee because fundamentally it's an MCMC method. So we can use all the guarantee that we have from traditional method. So one thing that I want to really highlight here is building black box is very easy, right? Like when you tell your students, oh, here's the data, go on PyTorch, train something, it goes, right? GPU do the work, the student didn't do the work. But it sacrifices some good guarantee that we need when we interact with fundamental science, like for example, accuracy, for example, convergence, for example, robustness, right? I'm a big fan of putting ML where it belongs. In the machine, like in the MCMC example, we didn't use machine learning to replace the entire MCMC or posterior problem. I use it as a proposal, which is where main complication are in, right? And I still retain most of the good properties in MCMC in that way. So I'm a big fan of building hybrid method, that's all I'm saying. So here are some takeaways. I think I'm pretty good on time. So first, don't forget your data, like when you're chasing out the model, right? I'm pretty sure, who's from CS here? Oh, yeah, like it's very, very common to, I've been interacting with like, I'm not to show them. I've been interacting with a lot of like people in CS that ask me for GPUs. Oh, this DSEI grid, we need a lot of GPU, we need to train the biggest transformer model, like scale and all that. And I understand, it's very hip, it's very easy to get funding. But don't forget about your data. If your data is crap, no matter how big is your model, I don't think it's gonna fly too well. Second, when people ask me to view the population Excalibur, which is like SPI for population thing, they ask for it, I viewed it, it worked, awesome. But then I need to tell them, wait. That's not actually what you want. I mean, it works, it passed all the machine learning usual check, your test loss awesome. But maybe they don't understand how machine learning actually works. Oh, actually, there's no robustness guarantee. Oh, actually, we just waste a lot of GPU. We just kill 3 polar bear. That's not good. The next thing is like for the student, more for the student is proving concept is really easy these days, right? I prove a concept again in the Fourier neural operator case for you, right? It works. No, it doesn't. Because ultimately, the scientists, when you work with fundamental scientists, they care about whether it push the accuracy down to what they want, latency down to what they want. Make it work. Make the software, all the engineering effort work, not just prove the concept. I mean, okay, fine. If your supervisor is like, we need to get this neural paper out, it's like, do it. But also think about how to make things go. Finally, try to view hybrid. So especially when it comes to interacting with domain experts, hybrid is awesome. I'll explain to you why hybrid is awesome. Because hybrid means that they usually have some crappy code, it's written maybe in Fortran or MATLAB. Then you just need to like modernize it, put some machine learning in it. Suddenly you have all the good problems. Instead of like just taking it takes more time, right? It takes more time than just running the legacy code, producing the data and train end-to-end machine learning. It takes some time to unfold them and see where to put machine learning. But do that. Try doing that. It's pretty useful. This is the main part. I still have one subpart, but before I go into that, any question? I have one crazy part after that.
I don't know if this is a good time for this question, but so it seems in the, I think, second part, you were talking about making the physical simulation more accurate, basically, right? But it seems like in the kind of generating process of this gravitational wave data, there's this other important layer, which is how noise appears, right, from the sensing process.
Right.
So do people spend lots of time modeling that more precisely? Because it seems also complicated.
It does. Like, and it's actually, that's where machine learning can come in to help. The way that people model is like now, you take a time series, make a really big screen like this one, put all the image in front and you ask the grad student which one of them is noise. And this really is, like, I mean, I'm bullshitting, that is like called data characterization. And there's like huge group in Caltech doing that. It's like, how is that reproducible and how is quantitative is not? Because it's just like look at the, and they even spawn like citizen science project for that. And I think that's where machine learning can come in because, yeah, that is a classification problem that you can be quantitative about it. But yeah. I told Carrie about this. It's like there must be chaos, and this is my liberty of like using it. This is something I deeply care. It has nothing to do with whatever I said before. But wasn't aware. I do high jump. So this is something I deeply care, and I think it's relevant for some of you. So high jump is like this sport that like you jump over guard. This is me. This is jumping over, I think, 195. So I do that a lot. Now, why am I talking about this? I'm shooting for LA Olympics. This is why I'm here. Okay, it's very important. Now, unfortunately, I'm not that young, but I'm still young enough to do it. But I think machine learning will give me an edge. I want to like just briefly talk about some of the machine learning things I've been doing. That I think is extremely fun. If you want to think about any of this, awesome. Let's talk. So one thing that I've been thinking a lot, I've been building like some computer. This is Sam's too. This is one video of me jumping in Eastern Campus. That video was trying to do some computer vision work on top of that. Okay, so there's like feature extraction thing and segmentation thing that need to be done. If you're interested in that, let's talk. Awesome. I'm building my whole camera system that I'm gonna set up. People are gonna think I'm crazy, which I am, but yes. So we're gonna do a lot of like computer vision works in terms of how to reconstruct my 3D body and stuff like that. Given cheap gears, I don't have that much money. Well, I was trying to like buy student time, but then I said I don't have money. But we'll figure something. But like the important thing here is so as an athlete, I don't want to think about the science all the time, right? As a scientist, I want to think about how to build things to make the athlete works better. And as an athlete, I don't want to think about that. So I've been building this pipeline that every time that I like take any of this, I take all my workout and build. I have like a database layer that I've built already myself, hosting in my home. I built a server for that. These are like different. You can't see very well, but key point annotation, classification, stuff like that. Timing and stuff like that. And I build this layer of like data lake. Basically, as a user, you want to just dump data onto the server, right? The second thing is this is the most important part of a data science project. It's called labeling the data, generating data. Okay, so I set that up, and it's a huge process for me to set that up. But labeling interface, label studios, awesome. If you want to like jot this down, this is your best friend. If you want to like think about a startup, it's like we need data. Like what do? Min.io Postgres. Awesome. And recently, this is something that I'm going to teach in my course. It's called Dexter. It's awesome. And basically, if you have data comes in, they will automatically trigger a bunch of workflow to like process your data. So we've been setting this up. ML ops. If you're interested in ML ops and all this like data stack, talk to me. I don't know, like this is formatting issue, but yeah, this is my stack right now. If you're interested in any of like these tools, not just like joining my project, but if you want to learn about how you can use this for your stuff, talk to me. Biomechanic. Like right now I have computer vision layer, like in the hardware like made, but later on I kind of want to generalize this to like some more principle thing that I like understand. Okay, is the force on my ankle bad? As I'm gonna like run a risk of injury. And this is Mujoko. Do people use Mujoko? Anyone do biomechanics here? I was hoping someone would do Mujoko, but this is something that I'm like really interested in. Anyone want to say, oh wait, that looks wacky, want to do it, we'll be thrilled to talk about that. By the way, this is like this is pretty fun. So Mujoko is like what DeepMind made. This is like a startup company that is trying to say that we're faster and more accurate than DeepMind. But they're closed source and I did pay them, so I'm not happy. I'm pretty stingy. So it's like, okay, can we do like open source code and you blast this is open source, this is not open source. Stuff. Anyway, so there's some research and solving ODE going into biomechanics. And finally, there's like some gambling system. Not really gambling, but you need to game So to get to Olympic, you need to be top 32 in the world, by scoring. And there's actually like a risk control problem to be solved. That's like, oh, should I go to, if I can, I go to the top competition, but I score 8, or should I go to like less well, shittier competition but get. But anyway, stuff like that. This is complete chaos, completely irrelevant, but I'm very into this one. If anyone interested in like ML ops stuff, I'm more than happy in the context of this, or how to help you out. Anyway, I think I'm running out of time. So thanks everyone.